Hello, Algebra 3. We are in Lesson 32. We're going to talk about inverse functions for a minute. Before we get started, I'm just going to go ahead and tell you this is going to be a slightly long one because we have a lot of material to cover. Inverse functions. So we remember the little function machine dealio that we used to do, right? So we would have a function. In this case, the function was y is equal to 2x minus 1. There's our function, right? So we could draw our function machine if we wanted to. Here's our x values. Here's our little function machine, 2x minus 1. And then this would be our y values, and it would spit out our y values over here. So let's say we decided to use 2, 4, and 6 for our x values. So we would put 2 in. 2 times 2 would be 4 minus 1, and we would get a 3 out, right? Put in the 4, would be 8 minus 1, we would get a 7 out. We put in the 6, that'd be 12 minus 1, we would get 11 out, right? So that's kind of the way it works. An inverse function is where we swap our values here. We're going to solve such that we find the y value instead of the x value. We find the x value by starting with the y value. That's how it's inverted. So the way we would write that is to solve for the x. So we would start with y is equal to 2x minus 1. And then we would get, we would add 1 to both sides. We get y plus 1 is equal to 2x, and then we would divide everything by 2. And that would give us x all by itself, and we would get 1/2 y plus 1/2. That allows us to plug in the values into y to get the x value. But that's not the way we solve, so we are going to swap the x and the y variable. Because the way our function machine is set up is you put in the x and you pull out the y. This is the inverse function to this. So we would do the same thing. We would put in x and we would have our value calculated, and then we would spit out a y. Same process. But what we do is we swap our x and our y so that we can do it correctly. So this would now be y is equal to 1/2 x plus 1/2. So we would put that in here, 1/2 x plus 1/2, and we would use our y values in our x system. So 3, 7, and 11. Well, 3 times 1/2, that's 3 over 2 plus 1/2 before over 2, that would give us 2. Okay, 7 in here, that'd be 7 over 2, make that 8 over 2, that would give us 4. 11 in here be 11 over 2 plus 1 over 2 be 12 over 2, that would give us 6. So you see how to go from one to the other in order to find, if we have our y values, we can swap it in order to find our original x values. Okay, and I know some of you guys are saying, well, why don't we just go the opposite direction instead of this? Because then we have to learn a different way to do it instead of just finding, using the same system and solving for y anyway. Okay. So let's look at the rules for this. And the rules for this is one, or the steps, I should say. We would solve the original equation for x. And then we would replace every x with y. With y, and then we would replace y with x. Basically, that means we're just going to exchange y's and x's. All right, so let's do, this was inverse functions. And that's how we would solve those. So let's do a couple inverse functions. Let's do 2 or 3 of those and see if we can get some practice figuring that out. All right, if you need to pause and take notes, do so. I'm clearing the page. 32.1. We're going to find the inverse function of y is equal to 2x plus 3. So our inverse function, we're going to solve for x. It's our first step. Step 1, we're going to solve for x. So that we're going to add, or actually we're going to subtract 3 from both sides. So we have y minus 3 is equal to 2x. And then we divide everything by 2. That gives us 1/2 y minus 3 over 2 is equal to x. Now we exchange the y's and the x's. We swap them and rewrite it. So that is going to be y is equal to 1/2 x minus 3 over 2. That's our answer. This is the inverse function to the original function. All right, that's what we're doing. Easy peasy. You guys can do these. 32.2. We need to find the inverse function of y is equal to negative 2x plus 5. So step 1, we solve for x. So we subtract 5 from both sides. Y minus 5 is equal to negative 2x, right? Divide everything by negative 2. So we have negative 1/2 y plus, because a negative over negative is a positive, 5 over 2 is equal to x. Replace, step 2, replace the y's and the x's, and we get y is equal to negative 1/2 x plus 5 over 2. So this is the inverse function to this function, and that's how we find that. Let's see, do we have one more of these? We do not. So you see how easy that is, right? That we're just figuring out how to write the inverse function of the original, and that is by swapping out the y for the x, solving for the x, and then swapping the variables so that we can write it appropriately. And then what happens whenever that is graphed, what we get, let's say on this one, we had y, we use a different color here. This was the original, black's the original. So we had y equals 2x plus 3. This is approximately, I'm not going to be exact, this is approximately y equals 2x plus 3. This is approximately y equals 1/2 x minus 3 over 2. So you can see they cross, they intersect, and they are going to have, of course, they're going to have the same degree here at the vertical angles, but they're not necessarily, they're not perpendicular, they're not, even though one would think they would be, they can't be because they have they don't have the opposite sign here, right? They have the same sign. So they're not going to be perpendicular to one another. They're just going to be 45-degree angles to one another. If they were perpendicular, they'd have that negative sign and they'd rotate all the way around 90 degrees. But this does not have that. So they are typically going to have a 45-degree angle to each other. All right, same thing happens over here. I'll do it in black this time. Here's our system. And then I'll do this like this. Y equals negative 2x plus 5. If we were to do that, we would see it here where it would cross really high on the y-axis. And that would be our, that would be 5 right there. And then it would be at the positive 5 over 2, which is 2.5. So it would cross, this one would cross right about yay. And would make a 45-degree angle right about there. And would cross at 2.5. Okay, so you can see where that, I didn't put my division sign here, did I? So you can see kind of where that happens. All right. Now, one thing to note about these is that they're going to kind of rotate around an axis of symmetry, and that axis of symmetry is your 45-degree angle, your y equals x. If I draw it right, you can see that this is the axis of symmetry here, and then this is the axis of symmetry here. But the rotation here occurs, I didn't draw it exactly right, this rotation occurs where the dot here is on the intersection point is on the axis of symmetry. I just didn't quite get my angles right when I drew that. But that is what happens, is there is some relationship to rotating around y equals x. All right, let's look at the hard part. This was the easy part for this lesson. Now we're looking at something that's going to be a little bit more difficult. You're going to have to really take some notes and pay attention here. So remember when we talked about quadrant signs in relationship to our angles? Let me give us a system here. All right, so let me draw an angle here. This is a quadrant 1 angle. Right, and within a quadrant 1 angle, we know that the hypotenuse is always positive regardless of where it is. And we know that the x-axis is positive here, and this is positive here, right? So what that means for us is that when we figure out, here's our angle, when we figure out the sine, right, let's do SOHCAHTOA up here, SOHCAHTOA, the sine of that angle is going to be a positive over a positive. And the cosine of that angle is going to be a positive over a positive. And the tangent of that angle is going to be a positive over a positive, because all of these measurements here in this quadrant 1 are going to be positive. So we can summarize this by doing the mathematical application. We're not doing a calculation, we're doing the application here. So we can say that, this is the note I really want you to take, that in the first quadrant, sine is positive, cosine is positive, and tangent is positive. All right, so looking at quadrant 2, here's our angle. Here's our angle theta. Well, this is negative, hypotenuse is always positive, and this is positive. So in this case, we have opposite over the hypotenuse for sine. So the sine here is positive. For cosine, we have adjacent over hypotenuse. So that's negative over positive, so the cosine is going to be negative. And then we have the tangent, opposite over adjacent, so negative over positive, so the tangent is also negative. All right, that's quadrant 2. Quadrant 3, that's here. We have this angle. And, oops, I accidentally made a triangle. That's okay. This is negative, and this is negative, and the hypotenuse is always positive. So when we do, here's our angle, theta. I'm going to get rid of that. So when we have our angle here, the sine is the opposite over the hypotenuse, so negative over positive. So that is going to be, sine is going to be negative. When we look at the cosine, that is adjacent over hypotenuse, that's negative over positive. So that cosine is going to be negative. And when we look at the tangent, that's the opposite over the adjacent. Tan is negative over negative, so that is going to be a positive. Again, I'm going to do another angle here. I'm not going to line it up so it won't actually make a triangle. Here we have positive, but then here's our angle. Our opposite is going to be negative. Our hypotenuse is still positive. So in the fourth quadrant, what we have for sine, we have the opposite over the hypotenuse, negative over positive. So the sine is going to be negative. Our adjacent over the hypotenuse, that's going to be positive over positive. So our cosine here is going to be positive. And for our tangent, we have the opposite over the adjacent. So that is going to be negative over positive. So our tangent here is going to be negative. Those things are important when we start talking about rotation of an angle. And that happens, we start looking for that when we don't really have a reference triangle and we don't know exactly where that angle lives on the quadrant map, right? So let me give you an example of that. Let's say we have a we're given a sine of an angle that is, I don't know. Let's say it's negative square root of 3 over 2. I don't really know where that is, right? I can draw a triangle and I can find a place where I have a negative over a positive for sine, but I don't really know what the values are here or how big that angle is. It doesn't fit into our reference triangle, right? I can't just plug it in somewhere. Now technically this is going to be our 60-degree triangle, but I don't know where it's located because sine can be negative in 2 different quadrants. So I don't know which is which means I won't be able to tell where it is on the map or what the degree of angle is. So I might spin around forever looking for that. In order to prevent that, we set limits. And the way we set limits is by saying I need a positive and a negative that are corresponding to one another for each sign or for each function. So that's what we're doing. We're going to set a limit, and that limit is called the arc. That is the limit. And whenever we put that on one of these with that capital A, that means I want to only find the angles that fall within these limits. And then that limitation is going to tell us what quadrant that particular angle lives in. So if I were to say the arc sine, I would want a positive and a negative that are connected to one another. So I'm going to use black. So that would be sine and sine. So that is a positive and a negative that are next to each other. And we usually want to start with this because this is where they're all positive and this is the easiest quadrant to solve because we don't have to worry about complicated calculations. So that limit, we know this is 0 degrees, this is 90 degrees, and this is what we would consider negative 90 degrees. That gives us a positive. This gives us a negative. So our limitations for arc sine, let me see the right way to write this. Okay, so the arc sine would be the limitations would be negative 90 is less than the degree of theta, which is less than 90 degrees. So it has to live in between these two. And is it equal to? That is the question. Yes, it is inclusive. It is inclusive. So it could be negative 90 or it could be 90. It could go anywhere from this line all the way around to this line. Okay. Our arc cosine, the limitations for that, put this in blue. For this one, we have a positive here, but this is positive. We don't want that. We want to go ahead and do a negative. So we have a positive and a negative right next to each other here, 1 and 2. So our limitations here are going to be 0 degrees all the way around to 180 degrees. And that's going to give us a positive cosine and a negative cosine, so we can solve for either situation that we are given. All right, and then our last one is arc tan. And our arc tan is going to be the same as our sine. We have a tangent here, that's positive, and right next to it we have a tangent here. Now, Miss Tracy, why wouldn't I go over here and do the tangent here? Because this is the way they told us to do it. If you can keep these numbers small, then that is the preference. You want to keep the numbers small. It's easier to calculate. So we are going to do between negative 90 degrees, less than or equal to, and then positive 90 degrees. And that keeps our calculations from getting up into the hundreds. We didn't have a choice with cosine. If this had been negative, we would have gone down here. But it's not. So it's the only one that has to go over here into the bigger numbers. We prefer to keep our numbers smaller, right? It just helps our calculations. And since we already have a pattern here with sine, it makes sense to stay with that same pattern for tan because we don't have to change as much, okay? We're keeping our numbers small and we're following the same pattern as something else. So these are the limitations that you need to write in your notebook as to where we can put these things on our quadrant map or our coordinate system to allow us to solve for these positive and negative creations. And you're going to want to put this part on here too, so you know which direction to flop. Notice we are not putting anything in the third quadrant. The only thing we're going to put in the second quadrant is the cosine. Everything else stays in 1 and 4. That makes it kind of easy to keep it all together. So let's do a little bit more illustration on this. Actually, no. Let's just do a problem and let's see if we can figure this out. So let me clear this. And 32.3. I don't think I want to do this in red. Let me go back to black. We are asked to evaluate the arc sine of the square root of 2 over 2. I don't recognize that, right? That's not one of our standard reference triangles. So my first gut instinct is to draw a triangle. It is positive and it is sine. So when sine is positive, that is, of the two quadrants we can use, that's the first quadrant. Okay, so that means it's going to go right here. Now I can take this and I can figure out, I can manipulate it by putting this square root of 2 back in the denominator. I can say square root of 2 over 2 times square root of 2 over 2, or I'm sorry, square root of 2. And that gives me 2 over 2 times the square root of 2, which simplifies into 1 over the square root of 2. Okay, well, I know what that one is. So that one is going to be right here. It's my reference triangle. That is going to be a 45, 1, 1 square root of 2. This is 45 degrees and 45 degrees. All right, so the sine is opposite over hypotenuse. So the opposite over the hypotenuse is 1/2. So the arc sine here for a positive is going to be a 45 degree angle. That is what I'm looking for. All right, so not a whole lot of math, just trying to relate it back to my reference triangle. And because I recognized this, I was able to resolve it and recognize this. That gave me my reference triangle. So always have your reference triangles drawn somewhere like inside of your back cover of your notebook so that you can refer back to them. So you can look at these values here and see for yourself. We know this is a sine of 1 over square root of 2. You should have somewhere that the 45, that would be a 45 degree angle. Sine of 45 degrees is equal to 1 over square root of 2. You should have that written down somewhere, right? You have your reference triangle, and if I were you, I would just write it next to the reference triangle. I'd write the sine of all of the angles that you have, right? 1 over that. The cosine of 45, you would want to write that would be the same thing. And then the tan of 45 would equal 1 over 1. Because that would be opposite over adjacent. So if you have that with your reference triangle, maybe even write that and then draw your reference triangle around it so you have it all in there. Then whenever you see one of these, you can quickly go and say, oh, well, that's a 45 degree angle. That's what that is, right? Because it's the sine of that degree, that's 45 degrees. So if you have that reference, then it's not even an issue. All you have to do is kind of get this manipulated into something that you can recognize. Now, there are going to be times when you can't recognize it, and then you have to do it the long way. But if you have something that you can play around with and pull it back into one of these reference fractions, then you don't have to solve it any further. You can just pull it off of your reference chart and be done. And that's why we gave those to you. So let's do 32.4. And this one says to evaluate the arc tan. So we're going to use our limitations of negative 1 over 3 times the square root of 3. Okay, so he's just messing with us at this point. He's trying to just trick us here. We know we can just multiply this. So the arctan of negative square root of 3 over 3. We can resolve this. We know how to get rid of that and kind of reduce it. So that's going to be times the square root of 3 times the square root of 3 is equal to 3 over 3 times the square root of 3, which resolves to 1 over the square root of 3, which we recognize as our 30, 60, 90 triangle. All right, so the tan, where tan is negative, is this quadrant right down here. So we would draw our 30, 60. The question is going to be, which angle is it? Which angle is the tan here? So we know that our reference triangle, let's say this is the 60, this is the 30, this is the 90. We know it's 1, 2, square root of 3. That's our reference triangle. We need to know which, is it the 30 or is it the 60? All right, so let's look at it. And if it's the 30, the tangent is going to be opposite over adjacent. So that's 1 over 3. The tan of 30 is 1 over the square root of 3. And then you could have all your references here too. The sine of 30 is going to be 1 over 2, and the cosine of 30 is going to be square root of 3 over 2, right? So you want to write all those down next to that reference triangle so that you have that. And then you have that other degree of measure here, the 60, so you'd want to do those too. Tan of 60 is equal to opposite over adjacent, so the square root of 3 over 1. The sine, or you can do it in any order, sine, cosine, tangent, whichever one you want to write it as. So the sine is the opposite over the hypotenuse, so square root of 3 over 2. We've already been through all of these, but I'm just refreshing your memory. And then the cosine of 60 would equal the adjacent over the hypotenuse, so 1 over 2. All right, so you want to have all of those next to your reference triangle so that you don't have to figure them out every single stinking time, right? So you can just flip and look. So this tells us, though, which one we want to use. We're looking for the tangent. That is 1 over 3. That's going to be this one. But it is a negative 1 over 3. You got to carry that negative every time you go. So negative 1 over 3, I know it's going to either quadrant 1 or quadrant 2. In quadrant 1, everything is positive. So that means it has to be in quadrant, not 2, quadrant 4. This is 1 and this is 4. So it's going to be in quadrant 4 because that is the place where our limit says the negative tan lives. So that means it's going to be the 30-degree angle here. And that this is the 30 and this is the 60. So that means that this is, the hypotenuse is 2. This is the square root of 3, and this is the 1 right there. So that tells me the arctan of negative 1/3 times the square root of 3 is equal to negative 30 degrees. Now, you could also write that in the positive format. So you'd start at the X and go all the way around to here, and that would also be a positive 330 degrees. Okay, if you measured from here all the way around the way we are supposed to. So there's 2 degrees that we could write. We could write the negative 30, or we could write the positive 330. Now he only gives us the negative because that's what he asked for here, but these are the same degree of measure. Let's do one more. 32.5. I'm going to clear this. 32.5 says we want the cosine of the arctan of negative 3 over 5. Well, guess what? That's not in any of our reference triangles. So this is an unknown degree of measure. So we've got to figure that out. So we are going to, first of all, look at the sign here. This is a tangent, and it's negative. So this is going to be in quadrant 4. That is where that angle lives. So we are going to approximate. This is -3, so it's going to be down 3, right? Is that right? Yes, it's going to be down 3 because tangent is going to be opposite over adjacent. So that is going to be, if this is our degree of measure, then the opposite is -3. So that's going to be down 3. So 1, 2, 3, right? And then it's going to be, the adjacent is this side, and it's positive. So that'd be 1, 2, 3, 4, 5. So that means it's going to live right there. That is our triangle. So we've got to figure out what all that is. So this is -3, and this is a +5. So we need to find our hypotenuse here so that we can figure out all of this. So we're going to say c squared is equal to 5 squared plus -3 squared. C squared is equal to 25 plus 9. C squared is equal to 34. So C is equal to the square root of 34. Now we have our length of our hypotenuse. And we don't need to find what this degree of measure is in order to find the cosine of this angle. Because now that we have all 3 parts, we could find the cosine of this triangle without any problems. All we have to do is put in the values. So the cosine is going to be, that's adjacent over hypotenuse. So all we have to do is find the adjacent. All right, I'm going to erase this right here because it's in my way. We find the adjacent, and the adjacent of this angle is 5. And the hypotenuse is square root of 34, right? This is positive. Hypotenuse is always positive. So therefore, the cosine is positive. That is how you would solve that. Not super complicated in regards to the amount of math that is required. You've got to understand where it lives, right? We're putting it within the limitations given by this arc here. This is saying it's got to be in here somewhere. One of these two. We're not going to play willy-nilly all over the place and have multiple responses. We just want to narrow it down a bit. And that's what arctan does. That's what the arc does with the capital A. Arc narrows it down. Now, if arc is written with a lowercase, doesn't mean the same thing. That means what are all the possible arcs. So this could flip anywhere. This would be a positive and this would be a positive. We could flip it. So we could flip it this way and this way, which it could be both of these degrees of measure. It could be a +30 if this is 30 or a -30, depending on what it is. So fortunately for us right now, John only uses the positive. So we're only worried about the limitations that we're given. We have one more to do. 32.6. We're going to evaluate the sine of the arc cosine of 2/3. Again, not one of our reference triangles, so we have to figure out where it lives. So the cosine here is positive, and the place where the cosine is positive is in the first quadrant, based on our notes. So it's going to live here. So we're going to do cosine is ca, right? So cosine is adjacent over hypotenuse. So that is going to be the 2 over the hypotenuse of 3. So we have, here's our angle. And I'm going to make those little spaces bigger so that it is easier to see. So the adjacent side is going to be the side with the angle. So 1, 2, and the hypotenuse is 3. So I'm going to take a guess here. And I'm going to just kind of draw it up here like this and bring it back down. And this is 3, and this is a positive 2. We don't know what the adjacent side is. I mean the opposite side, not the adjacent side. The opposite side. So that's what we've got to do. I didn't have my theta in the right spot. So we've got to find the opposite side in order to find the sine here, because sine is opposite over hypotenuse. So we know it's going to be something over 3, because that is, I don't know why I wrote hypotenuse here. That should be 3, because that's what we're given. Cosine 2 over 3, which is adjacent over hypotenuse. So it's going to be something over 3. That is going to be the sine of the cosine 2 over 3, something over 3. So let's find the opposite. We can do that with Pythagoras theorem really easy. That's what we're going to use. So we have 2 squared plus the opposite squared is equal to 3 squared. So 4 plus opposite squared is equal to 9. Subtract 4 from both sides. The opposite is going to equal the square root of 5, because 9 minus 4 is 5. We unsquare both sides. The opposite is 5. So now we can put this in right here, square root of 5. Now we can find the sine, square root of 5 over 3. That's it. That's all we had to do. So this tells us where it lives based on what the cosine, what that means. And we figured that out here, right? We knew it was positive. We knew that cosine lived in the first quadrant when it's positive. And we knew that that was the adjacent over the hypotenuse, which allowed us to draw our little thing here. So we could find the opposite side, right? And that gave us the illustration we needed in order to do Pythagoras theorem the right way and solve for the opposite side. Now, you're going to get to the point to where you know what this means, and that is the goal. The goal is to get to where I can show you this and you don't need to draw this. You can say, I know that this is adjacent over hypotenuse, so adjacent would be one of the sides, don't know what the opposite is, and the hypotenuse is 3. And then you solve it, and you're able to put it in sine format because you are looking for this degree or this measurement here to go here. That's the goal. The goal is to get you into this such that you don't need the illustration. You can just do this part and this part almost in your head, right? You put it on paper, but you don't need to see the illustration. That's what we're trying to do. We're trying to get you to the point where you can see all of this stuff and understand where it lives. And that is the last problem we have for lesson 32. I will see you in lesson 33. Questions, questions, questions. Please ask, message, holler, phone call, text.